Hello there, and welcome back. So for today's lab, we're going to go over an image captioning with visual attention. And to just summarize, the idea here is that uh, we have images and we want to build some sort of like a generative model that could look at the image and basically describe what it sees in the image as like a caption for the image. So this model architect basically comes from the attend and tell basically paper. The overall architect it's looked like something like this. In order to understand what we are going to develop, let's first break down the architect of the model. So you can think about of this model as two separate processes. One process is, or one model is that we have an image, as you can see here, and we need to convert that image into some contextual representation. You need basically, that means that we need to find important or important basically contents that are within this image using some image processing basically models. Now you can basically develop your own basically sort of like a convolutional based models here. But for the purpose of this lab, what we will do here is that we are going to use MobileNet as a pre-trained model that we are going to use. So MobileNet is this corner here. Image goes to the MobileNet, and as an output, we will get uh, the last basically representation of the MobileNet, not the final output, because the final output is like it's maybe for downstream tasks, for example, classification. We don't want that. We're only going to get the one before the final output or the last representation. That matrix is going to be the contextual representation of the image. So that's going to be the first part of the model. The second part is we need a generative model. And for the purpose of this lab, we are going to do something like a decoder section of the transformer. So we don't have the encoder, it's going to be just decoder. And important part about decoder is that the decoder of the transformer is that it's a generative model. That means it's start by one token and make a prediction, goes to the next token, uses the previous two tokens, make a prediction for the third token, then use the previous third token to make a prediction for the fourth token, and so on, right? So what we need in order to create a decoder is going to be, first we need basically some sort of masked self-attention. Okay, why masked? Because we want to ensure that if we are predicting the word at index number 3, we are not attending any words after. We only attend to the words that are coming before that. That's the concept of like a masked self-attention, right? So we're going to have a masked self-attention with proper normalization and basically adding a dropout. After that, we need to after we did this massive attention, we have some sort of like query representation of what we have right now. Now we want to enhance our basically work by attending to the image that we have. That means what we want to do something called a cross attention. We basically doing a cross attention from our decoder to the output of our encoder, which is the MobileNet's basically output. So that becomes our third steps in the decoder. Is going to be cross attention. And after we did the cross attention, we do some basically normalization, add the residual connections, and then we go for prediction, which just becomes word by word prediction. Okay, so that becomes the overall architect that we are going to develop for this lab. And the idea is that to have something like this, for example, if you see this image and the model be able to produce something like a surfer is surfing on a wave, so on. And what you can see here is that these are the attention weights that, for example, we are visualizing. And the goal here is that your model, for producing a certain word like a surfer, your model should have attend to the location in the image where the surfer basically is based on. Okay, so that's the overall goal that we have. Now, there are a series of pre-processing and libraries that I'm importing for this labs. those are not part of the those are not the goal of this walkthrough video. But what we do is that all the codes are available. I highly recommend you to take a look at those. So there are two data sets that I found that be interesting that we could work for this lab. One of them is the Flickr 8, and the other one is the basically Cocoa captions. So for the purpose of this lab, I'm using the Cocoa, but the code for downloading basically both of these are again part of the lab, so you can basically access those. I'm only getting the 10,000 basically images from the Cocoa for training and 5,000 for validation. I have already tested out with larger amount of data, and it's giving you a better result. But for the purpose of the lab, I'm only using this 10,000 because it takes a longer time to train a model. So the data when you get from this, like the Cocoa basically data set that you get has basically has an input, which is an image, and it also has a caption for the image. Okay, so you basically will see that there is an image, this image, and there is a caption for that image. Okay, so the first thing that we want to do is that we want to pass the image to a mobile net and get the contextual representation. So in order to basically use mobile net, what you could do is that you could basically import mobile net, and here I'm using the v3 small. You pass the image shape. What is the image shape that you are passing to this mobile net? And there is a parameter here called include top. You need to set that to false because you don't want the output of the mobile net. You want the basically output of the layer before the last layer, because that's the contextual representation. So you set the include top to false, and you say that include the pre-processing also to true, and you set your mobile net to not to be trainable, because mobile net is a really large model, is already pre-trained, so you don't need to train that, at least not for the purpose of this lab. So you set mobile net trainable to false, so that doesn't slow the training process that you have. So if you pass an image to the mobile net, our image by default from the Cocoa, they are 224 by 3 channels. When you pass it to the mobile net, the output that we will get is going to be 7 by 7 by 576. Okay, so height and width are 7, and the depth is 576. So the next thing we are basically introducing tokenizer. Why? Because right now the first part is done. So imagine you have the image processor that basically processes the image for you. But for the second part, for the decoder, is that we need to basically deal with text, right? So there are two things here to remember. One is that the text that we have, as we saw, every image has a caption. It doesn't have a label at the moment, so we need to convert it to a label. And because we are building a generative model, and this generative model are basically autoregressive, that basically do sequential prediction. So every word, if you shift your text by one index to the right, then that you can use it as your basically label that you want to predict. As an example could be that if we are, for example, looking at this caption, a very typical bus station. At first, basically when we shift this to the right, that means when we want to predict the word A, okay, first the first token that we are using, let's say for example, we call this start. So we have a start as a token, goes to our generative model. And the generative model, for example, produced the word A. And A also is the label because we have shifted. Then when we want to predict the next word, now we have something like this. These two go to our generative model. And the label that we want to predict is very. Okay, so we basically make a prediction and we compare that whatever we predicted with the word vary to see that how much we need to adjust during the backpropagation. So in order to make the labels for the generative model, again, all you need to do is that shift your text as a tokenized basically text by one indices to the right. Okay, so in order to do that, first we basically create a text vectorization. We define a vocabulary size. We say that let's standardize it. We adapt that to our training data. So basically, this is basically the example of the dictionary that we will have. we basically, when we tokenize this, now basically we have also this, token representation. So then we introduced two layers by TensorFlow, a string lookup and basically the reverse of string lookup. So one of them basically maps word to indices. So that means map any word to proper indices. And the other one does the reverse, maps indices basically to word. Okay, so let's go down here. Just basically an example of we basically creating these patches of the data, and again the match shapes basically is the function is already there. But what we want to do is that we want to be sure that there is a one-on-one basically image to caption basically example. So again, this function prepare data set and all of those are in the helper function, so you can basically review those. But what the prepare data set does, you pass the image and the caption, and it returns you three outputs. One output is the image. The second output is the caption for the image. And the third output is going to be shifted captions by one indices, which we are going to use it as an basically target or labels for the generative model that we have. Okay, so we converted image and a caption into three data points. It's like an image itself, the caption, and the shifted caption by one indices. So that's kind of like becomes our target. I put also this function here as like that helps you with, because some of this processing takes time, so you can save the data and you can load the data later. Okay, so I'm just going to go here back to the transformer model, and let's start to see what we need to build such model. So we're going to go over the decoder part, not the encoder part. So we're going to just focus on building the decoder section. So in order to do that, one thing that's really important is, and you have seen this as part of the transformers, is that the challenge with transformers is that the sequence order basically technically doesn't matter. And in order to enforce the basically the sequence order, that sequence order means that the sequence that the word basically exists in the document. In order to enforce that or make it important, we need to add some sort of like a positional embedding or sequence embedding. For the purpose of this lab, I'm just only using sequence embedding, which is just more straightforward. And in order to do that, so we're going to create a class called sequence embedding. This sequence embedding, what it does, it basically looks at okay, what's the basically first let's rephrase this. Sorry, so we're creating an embedding. This embedding has the maximum length, like what's the maximum length of the sentence that we have, and depth also. The depth basically becomes the embedding depth that you have for every word. And then we have this token embedding, which basically we have a vocabulary size and we have the depth, and we apply mask to 0. That means if there's a padding, it basically masks. So, and then we also have this layer add, which is simply an additive layer. So we created 3 layers here as part of the init. Then we create this call function. As part of the call function, the first thing that we do, we get a sequence, which is, again, this is part of the generative model. So there is no image here. So we get a sequence. A sequence is the captions that we have. Sequence has the following dimension: batch, sequence, and depth. Okay. So what we do here is that we basically convert basically a range of tensors. That we say that, hey, I want to have this tensor that goes from 0 all the way to this basically sequence range. That's how many sequence basically we have. Then we add additional dimension to that, and we pass that to the positional embedding. And positional embedding basically creates this positional basically representation of the text. What we do here is that we add that positional vector representation to the data itself, to the sequence data after the embedding, and that becomes our basically data. You can think of this as like a simple scenario is that if I have the following sequence, a simple scenario is that you can basically think of this, that we are creating this positional embedding of like 1, 2, 3, 4, and we basically ensure that we add this to this. However, you cannot directly add this to this, because again, this is just a vector of words. So what we have done is that we first converted those using our text vectorizer. We converted to like a numerical representation. So let's say these are what we have. So just random numbers. Sorry. Let's say this is the vectorized version of this cat, this sentence. The next thing is that we pass this vectorial representation to an embedding vector. So embedding vector has certain dimensions. So you can basically, what we will end up with is, so if we have 5 words, we end up with a matrix of basically 5 by the basically depth. What did we use here? Sorry, depth. Okay, so this becomes by depth. Okay, that means a word A will be converted into some numerical representation using embedding that has lengths of depth. It has basically, let's say 0.2 and so on. It has D of those in it. And the same for cat, we have D numerical representation. For on, we have D numerical representation. So this becomes 5 by D. So when we want to add this, basically embedding positional representation, we need to be sure that, for example, if we want to add a value of 0 to this vector, it will be added to every element of this vector. And if we are adding 1 to this vector, it needs to be added to every element in that, and so on. So that's basically what we did here in sequence embedding. So we converted the basic text into some vector representation, then embedding. Then we added a basic positional positional encoding to every element of every embedding of every word. Sorry, that's a little bit crazy. So the next step becomes the what we say the mask, basically self-attention. We call it here causal, basically self-attention. And what we need here is a multi-head attention. So the first step is that, because it's going to be a self-attention, we want it to be a multi-head attention. So we create a multi-head attention, and we also, after that, we create a add layer, which just does the add processes for us, and we add a layer normalization, basically to ensure that we keep the basically something like internal covariate shift of the data constant, or like we have a proper distribution as we go through the layers. So then what we do here is that this class, when it gets a data, it basically gets the sequence. It basically passes the sequence to the multi-head attention. The sequence itself basically becomes key and query, query value and key technique at the same time. And then we set that to use a causal mask. The next thing is that we basically do a residual connection. That means whatever is this attention that we get, we add the data back to itself, which is, again, is a good practice to avoid basically losing information as your model becomes larger and larger. So you have these residual connections. And then after that, we apply a layer normalization. So this part covers this section. Okay, so this is what basically we are doing here. The causal, or basically multi-head mask self-attention. The next thing is that we want to have a cross attention. That cross attention basically is the part that we basically for every token that we are our generative model is predicting, we allows it to attend to every basically location from the image, in order to make the prediction for the next word. So that becomes the idea of cross attention. So in order to do cross attention, we again create a multi-head attention here. We do the same thing. We add basically some add layer. We add a normalization layer. One thing here we need to do here is that if you think about the output of sorry, this is the best image. Here. If we think about the output of the mobile net, so the dimension that mobile net produces, the depth is 576, okay? And the dimension that we are using as an in our embedding might not be 576. It's probably some much smaller. And for this lab, we are using something like 256. So if you try to do cross attention, you have dimension mismatch. So you cannot do that. So what we do is that we ensure that this image, this like a contextual representation, has the same depth, dimensional depth, as the output of our multi-head attention or the causal attention. Okay, so in order to do that, what we do, again, sorry for scrolling up and down here, we are adding one dense layer. That dense layer job is that basically to ensure the image from the depth 576 will map to how many units or what's the depths that we have as part of our output of our causal attention. So this function cross attention as an input gets x and y. Here x basically is the query, the word that basically, you know, the current word that we have, that's the query. Y is here the image. Okay, so x is the current at time t, for example, 1, the word a is our query, and after going through the causal attention, and y is the total image basically that we have. So the first thing we need to do is that we need to pass the image to this layer that we just talked about to ensure that our image has same dimension as the text embedding that we have. Okay, so that's basically what we do here. The next thing is that now that we have a same dimension, we basically call to our multi-head attention layer. We pass the text, the query basically that we have, and the image, and we say to return the attention score for us. So it gives us the attention output and the attention score. Then I save that attention score into this basically variable in order to be able to access it later. That's the only reason. So the next thing is that we want to add a residual connection, again, to ensure that, you know, the data doesn't get lost. So basically we add our x, which is the query vector, back to the attention output that we got, the output of cross attention basically. And then we do a layer normalization on that. So this basically gave us the cross attention part. Now the next thing we want is that after we did cross attention, because we have some downstream task that we want to use, and in our case, our downstream task is text generation. So we need a fully connected model basically that helps us with that prediction of the next token. So we create a feed-forward network. It has 3 fully connected layers. First one, basically 250, that has certain number of, depending on if we are using 256, so it's going to be 512 nodes, activation ReLU, and then we get from 512 to 256, and then after that we add basically some dropout rate. Okay, so and then we do a layer normalization. So we haven't done any softmax here. We will basically add that later. So when we call to this feed forward, what it does, it basically has that what do we call it? It has that input, which is the output of cross attention layer. It passes that to this fully connected layer. Then it does a residual connection again to ensure that the data, you know, doesn't get lost as we go through this many layers, and it does a layer normalization on it. Okay, so that becomes the if we want to go back to the image again, sorry for that, it becomes this section that we have. Okay, so let's go back here. We go to decoder. So now we're going to basically wrap all of those together, and we call it a decoder layer overall. So decoder layer, what it has the causal attention, it has cross attention, and it has the feed forward in it. So that becomes, we put all of those on top of each other, stack those on top of each other. So the self attention, we call to the causal attention that we created. For the cross attention, we also call to that cross attention, and for the feed forward. So we have 3 basically models here, what we call the stacked models. Self.cross attention, basically self attention, or causal attention and self.feedforward. Now, as part of the call function, when the input comes to this decoder layer, the input basically has two parts: image and the caption. Okay, so we pass the caption basically to the self.attention. We pass the image and the output of this self-attention to the cross-attention. And then we pass the output of the cross-attention to the feed-forward that we have here. And here, again, I'm just keep tracking of the last attention score for visualization later. And we return the output sequence. So the output of this decoder layer now is going to be because if you go here, so basically what we have here, we have a layer normalization. So it's going to be this layer normalization over basically a dense vector. And the dense vector has, let's say, unit, we have 256. So the output basically is going to be a vector of 256. So the output of the decoder layer. Now, the challenge here that we might have, as when it comes to a generative model, is that when you try to, when the model basically tries to predict the next token, we want to ensure there are some guardrails around what tokens that we don't want the model predict, and for the purpose of this task, we don't want our model to basically generate text and put tokens like empty or unknown or start. We basically want to enforce some rules that the model basically does not basically predict those tokens. One simple scenario is that you basically could just set high negative value for these tokens and don't let the model to predict that. Remember, at the end, for the token prediction, we need a softmax basically layer that gives a probability of what's the highest, what's the next token should be based on which token has the highest probability. So if we enforce a large negative value for this tree, the model basically always will assign a probability of 0 to those predictions. The other scenario is that we can do some sort of like a smart initialization, and basically what we could do here is that if we just ask the model to make prediction, all the tokens could have a uniform basically probability or uniform distribution basically of coming next. But what we want to do is that because the reality that actual tokens distribution are not uniform, so we want to enforce some sort of additional basically information. So it's not a uniform basically distribution. So what we could do here is that we are going to use a concept like the entropy and negative log to improve the next token prediction. So we're going to create this class called token output. Basically, this token output, we're going to say we're going to ban these 3 tokens. We don't want our model to predict those 3 tokens. This basically token output is the last layer that makes that prediction. What's the next token that you want to predict? Which basically is going to be some sort of let's think about like a softmax prediction. So we start with basically having a dense layer, and we say that this dense layer, the output of this dense layer should be how many unique words basically we have in the vocabulary. So that becomes the size of this dense layer. We are going to introduce a bias term to help us adjust the value for every token. So if we want to ban a certain token, we basically added a really large bias value. Now, basically here, what as like a smart initialization, what we do, we're going to, instead of forcing those values directly, we're actually going to learn from the data and vocabulary that we have. So basically, we go over the vocabularies that we have. We count how many times this vocabulary was repeating in our training data set. So basically, this part, we do the count. And then we calculate the probability of each word, because if we have the counts for every word, we basically do what was the count divided by total count. So we get the probabilities. Then we get the log of the probabilities. Also here, we set the, if the count was basically, count area was 0, we set that log to be, to probably to be 1, because that way the log of that becomes basically 0. We calculate the entropy. This is the entropy of the probability of words. And we're also going to predict it. The uniform, basically, entropy becomes like this if we just assume it's uniform. And if we do marginal entropy, this is going to be the value. The next thing is that we basically, we are going to set the bias to be equal to the log probabilities that we found. So for every word, we have a log probability. Okay, if the probability of, if the count for example, a word in a sentence basically is 0, we assign the probability of 1, so the log of that becomes 0. So the bias term for that token becomes 0. All right. So what the next thing we do here is that we go over this self-bias that we have, and we set the bias value for the band token to a really large negative value. So that way, basically, it's just, we ensure that they are not going to be predicted as a next token. So, and as part of the call function, basically here we again we call to the dense layer that we defined here, which converts the tokens basically into converts our data into a vector of size of the vocabulary that we have, and then we add bias term to that vector representation. Okay, so that becomes the output of this token. If you apply this, for example, in our data that we have, we will see that the uniform entropy was this. The marginal entropy is basically as this one. Okay, and again, remember the entropy is some metric, sort of like amount of randomness, basically, that you have. So here we have more like a smart initialization. So it's like the amount of randomness is much lower in the marginal entropy. Now, we're going to put all of this together, and we're going to create a model called Captioner here, okay? And the idea of this Captioner model is that it basically gets the data and it processes it. It starts with the image, convert the image to embedding representation, then picks the caption, and one word at a time basically makes, one word at a time, it wants to make it predict what's the next token that we need to predict, and it goes through the process that we defined, which is going to be causal self-attention, it's going to be cross-attention, it's going to be feed-forward, and it's going to be next token prediction. Okay, so we're just going to put all of those together in one function. So this function as an input basically gets a tokenizer, feature extractor, which is going to be our mobile net, the output layer, which we defined here. This is the output layer, which is a token output. Number of layers is defined like how many layers you want to do as part of your training. Units, max length, number of heads, drop out. So we're going to basically initialize all of those in the following format. So we also create the word to index and index to word here. We have sequence embedding. And then for the decoder layer, so if you say I want to have 2 layers of decoder, so basically it basically creates 2 of these decoder layers. Just the more layer that you have, at least the way that I tried those, actually increases the chance of overfitting. So just be sure that you look at, you're careful with the number of layers that you're using. If you want to play with a parameter that gives you better learning, mainly the number of heads, it gives you better representation in compared to the number of layers. And again, just as an experiment here. And we have the output layer. So here what we do, we have this call function as an input. Every input has an image and then has a text also. So we extract the feature from the image. We basically reshape the image to the to have the following basically dimension, and we basically tokenize the text that we have. We pass the text to a sequence embedding to add positional embedding to it, and then for every layer in the decoder layer that we have defined, we pass the image and the text to the decoder layer. And decoder layer, if you remember, it itself basically does series of process. It's like a causal attention, multi-attention, and then we return the output, basically the output of the decoder layers. We pass it to the output layer, and that's what basically we are returning. There is this function that we also put here for you. It's called simple generator. What it does basically, it says that, hey, I want to just greedy start generating tokens. It has this parameter for a given image, so it has this parameter temperature. If you set the temperature to 0, it becomes a greedy next token prediction. That means the model picking the most likely next token. If you increase the temperature, it adds more basically randomness in the output of the model. It's just for you to practice. And then we go here. So we start, we initiate our model. So this captioner model that we did, this class that we defined here, we're going to initialize it. We tell to this captioner, we have a tokenizer. Our feature extractor is the mobile network that we imported before without the final layer. And then we have also this output layer that we defined above. How many units we want to have, what's a dropout layer, what's the number of layers that we are going to use, and what's the number of heads that we are going to use. Okay, so for the purpose of this lab and to make it easier to train, I'd set this to 5 and 1. That basically here, this one example that we get from the data set. So this is the data that we see, the image that we are seeing. What we want to do is that we want to first train the model. However, we need to specify basically certain basically loss and metrics for the model. So here, what we do, we are going to introduce something called mask loss. Basically, the benefit of mask loss is that we basically remove certain tokens, from calculating the loss. So that's the goal that we have here. So we are doing a cross entropy with logit, and we are basically anytime that the labels are not 0 and basically the loss is less than certain number, we basically create this mask as like it's going to be true, false. We apply that mask to the loss that we have, and then we calculate the basically mean loss. So we drop out certain basically prediction technically. And then we do the same thing for mask accuracy by dropping out certain basically prediction because they're not important. Because if you think about it, as a text generation, if your model produces lots of pad, for example, or lots of spaces, then that can increase automatically your prediction level or accuracy level. Then we train this model for certain number of times, and I trained it already because it took some time. This becomes the validation loss and loss. If you play around with the number of head and let the model train more for you, add more number of training data, you will get some improvement. Then I try out the model for one image. That's the image of that above that we saw, and the model predicts this caption, person and person in the match. I know that it doesn't make much sense, but again, you need to let this model to run for a longer time. And we also, as you go down, we can basically look at the attention weights per token, and to see that we're for producing every token, which position on the image the model did attend to. Okay, so that basically becomes this. We also could add this function that when you run the model at the same time that it makes a prediction for the next token, it also can visualize the embedding at the same time for you. Okay. Overall, I will highly recommend you run the lab, try out with different parameters, try out with different number of heads, try out with a different number of layers, and see what you will get. I hope you enjoyed the lab. Thank you.